Okay, so let's go ahead and finish this problem, number 4. So we've already established a few things here, but we are trying to find the volume that lies above the cone and below the sphere. So kind of the highlighted area is in here. We are trying to find all of this space in here. So it's got to be above the cone and below the sphere. And we already established where the sphere was by doing all the algebra that we see on the left-hand side. We know it's a sphere that has been shifted up 2 units with a radius of 2. So one thing we can clearly see, and we started to kind of write this earlier, one thing we can clearly see is that it goes all the way around, so theta is going to go from 0 to 2 pi. Okay, we know just from the information that was given that the cone itself is phi equals pi thirds. So phi opens from the z-axis out to pi thirds and stops. So we don't really have much of a choice there. And not z, and rho, well, the smallest that the smallest this thing can be is 0. Right, rho can be as small as 0, and it can go all the way out to the edge of the circle. That's the furthest that it can go out. So the edge of the circle, in this case, the circle was given to us as rho equaling 4 cosine phi. And in this case, it says find the volume, so the density would be 1 here. So we're just going to do our conversion factor, rho squared sine phi d rho d phi d theta. All right, and then from here, it's just doing the integration. So we don't have constant bounds everywhere. So we are going to have to do the first part with respect to rho. So we should get 1/3 rho cubed sine phi d phi. Oh, sorry, forgot the bounds. From 0 to 4 cosine phi, and then d phi d theta. So plugging in 4 cosine phi, 4 cubed is 64, so we get 64 thirds cosine cubed phi sine phi d phi d theta. Now we have constant bounds. These are separable because all I have left is phi. So we can go ahead and do our d theta from 0 to 2 pi, which we know, of course, is just going to give us our 2 pi. So we're done with that part. And then we're still going to have to do this integral. That's a cube. All right, so we can pull the 64 thirds out to the front of this thing. And that's going to give us, what, 128 pi over 3. And then the integral. And we're going to want to do a U-substitution on this thing. So U, in this case, you don't want to let U be sine because you're only going to be able to get rid of one of those 3 cosines. So you want to let U be cosine in this case. So U is cosine phi. Du is negative sine phi d phi. So d phi is du over negative sine phi. And I am going to change the bounds, but hopefully that negative will flip the bounds back over. I think that makes the most sense in this case. So if we change the bounds, plugging in 0 is going to give us 1. Plugging in pi thirds is going to give us a half. So yeah, the bounds are backwards, but the fact that we have that extra negative is going to help out. So this is going to be u cubed sine phi times the new d phi, which is du over negative sine phi. The sine phi's cancel out. That negative is going to flip our bounds to 1/2 to 1. So finishing this thing off, we've got 128 pi over 3 integral of 1/2 to 1 u cubed du. So 128 pi over 3 times 1/4 u to the 4th from 1/2 to 1. So I can multiply the 1/4. So let's see, 128 over 4 is 32. So we got 32 pi over 3, and that's multiplying these two things together. And then 1 minus 1/2 to the 4th power is going to be 1/16. And of course 1 minus a 16th is 15/16. So 32 pi over 3 times 15 over 16. The 32 over 16 reduces to 2. That reduces to 5. And 10 pi. That's the volume that lies in between the cone and the sphere. All right, one more to go. Let's see, number 5 here. Let's see if we can get this one done in less than 10 minutes. And if you guys do 2 times speed, be in less than 5 minutes. Evaluate the integral by changing the spherical to spherical coordinates. So it does tell us to change the spherical coordinates. All right, so the first thing that I notice is that the dz is on the inside, dx then dy. So the dy and dx are our domain. So if I look at this in terms of x and y, first of all, it tells me that y goes from 0 to 3. So y is going to vary from 0 to 3, and the x part looks like it goes from 0 to the square root of 9 minus y squared. You should recognize that as the top of a circle with a radius of 3. So really, it looks like this thing, since y goes from 0 to 3, the x goes from 0 out to the edge of the circle with a radius of 3. Looks like it's right there. And we're only talking the first quadrant because y is going from 0 to 3 and x is going to the top part of the circle. So it's just the first quadrant there. All right, so we can pretty easily change that stuff into spherical. That won't be too difficult. Let's take a look at the rest of this. So the easy part is going to be changing this. Okay, we'll change that. That obviously is going to be rho squared. That'll be our density function. But the bounds. Now the bounds for z. The bottom bound for z is z equals square root of x squared plus y squared, which of course is z equals r in cylindrical. Okay, that's the same thing in cylindrical. If I want to figure out kind of what that thing looks like, because I have to figure out what these things are doing as far as the actual graph is concerned, if I change this into, well, don't change it, but if we square both sides of this one right here, that gives me z squared equals x squared plus y squared. You should recognize that as a cone, because if you subtract the z squared, you really just get a cone. And because this part over here was the positive square root of x squared plus y squared, it's the top half of a cone. And then the top one, the top equation, so we'll write this down. This was a cone. There we go. And then z also is the square root of 18 minus x squared minus y squared. So once again, the idea is if you kind of square both sides of this thing, and then add the x squared and y squared over, what you have is a sphere with a radius of, oops, forgot the square, with a radius of square root of 18. So I know that rho is the square root of 18 there. And technically here with the cone, rho is going to be 0. So I know going to spherical, those are going to be my rho values. I'm going to go from 0 to the square root of 18. Biggest thing is, now I know that, again, we've got this idea of a cone and some kind of a sphere that this thing is sitting um, underneath of. And this sphere specifically does not look like it has been shifted, so kind of draw that. The whole sphere is going to do something like that. But we're not interested in the whole sphere here. What we're interested in only is really, let's see, we said it was in the first quadrant, so this piece is actually going to project down into the first octant. So it's really going to be just projected down into there. This is the portion of it that we're looking at. The projection would come straight down from the edges. But it does say it's going to be between that cone and this sphere. So I didn't write the fact that that's a sphere. And it's not a sphere. All right, so we're in between the cone and the sphere, so we are talking about the highlighted area up in here, but we're only talking about it in this, like this region right here. That's kind of hard to do with my highlighter, something like that. We're only talking about that little space right there. So what we really need to find is we need to find the intersection of the sphere and the cone. Well, we know that the sphere is this one. And we know the cone is that one. So what we have, squaring both sides, see, we'll add the x squared and y squared from the left to the right. Oops, forgot the 2. Dividing everything by 2, looks like the intersection of these two things is that circle, x squared plus y squared equals 9, which is the circle of radius 3. So that's the intersection of those two things right there, which actually should make perfect sense. I guess we really didn't need to do that since this right here was 3 and this right here was 3. That makes perfect sense that that's where those two things intersect. So what do we know for our integral? Let's see what we need to figure out here. We know that this does not go all the way around. We're just talking about in the first quadrant. So theta up here is only going to go from 0 to pi halves. Phi, we have to figure that out. And we do know that rho is going to go from 0 up to the square root of 18. Okay, the original function was the density is rho squared. We have a conversion factor of rho squared sine phi, d rho, d phi, d theta. All right, so how are we going to figure out phi? How are we going to figure out the angle of Bloom, what this thing goes from? So just looking at the picture here, obviously it's going to go from the z-axis out to the green. The question is, where is that? So I need to put this into spherical coordinates. I need to put it in terms of phi. So I need to find some of the one equation or multiple equations up here, whatever I need, in order to actually convert this into terms of phi. What I know from here is that z equals r, both of which I can put into terms of phi. So I can actually figure out what this angle of Bloom is. It obviously is going to start at 0. That much we can tell. So the angle of Bloom starts at 0. But what I need to figure out is where it finishes, where the green line is. So I know that z, in terms of spherical, is rho sine phi. And I know that r, in terms of spherical, is rho cosine phi. Well, if you didn't already know, because these two things have to be the same, you can divide out the rho, and where is sine of phi equal to cosine of phi, you should know that that's pi fourths. But if you didn't, what you would do is you would divide both sides by cosine, and you would get sine over cosine equals 1. Tangent of phi equals 1. Of course, phi then would have to be pi fourths. So we're going to go from 0 to pi fourths. All right, and there's the setup. In this case, this is really nice because this time we do have all constant bounds. None of this stuff is going to be terribly difficult to integrate, so let's finish it off real quick. So we know 0 to pi halves of d theta times 0 to pi fourths of, in this case that's phi, so sine phi d phi times 0 to square root of 18 of rho to the fourth d rho. Alright, so the first one is just going to be pi halves. We have to do a little bit of work on this one. So this is going to be negative cosine phi from 0 to pi fourths. And this is going to be 1/5 rho to the fifth, 0 to square root of 18. Alright, so let's see. Pi halves times, plugging in pi fourths into cosine, we get negative root 2 over 2, minus, plugging in 0, we get negative 1. This one's not nice. That's going to be 1/5 of root 18 to the fifth minus 0. Alright, so let's see, after all said and done here, we are going to get, this one's going to become plus, that's 1 minus root 2 over 2. And then this one is going to be 1/5, let's see, if I actually wanted to simplify that, that would be 18 to the square root of 18 to the fifth, which is really 18 squared times another square root of 18. Let's not simplify it any further than that. Let's just make it 8 square root of 18 to the fifth. You could distribute the pi halves. You could multiply the 1/5 of the root 18 to the fifth through, but there's really no need to do that. So this would be that volume. I'm sorry, that mass, because we did have a rho in this case. All right, there you have it. Hopefully that helps you with the rest of the web assignment.